Hello everyone, today we will learn about the Hamiltonian dynamics. In Lagrangian dynamics, you have seen that your Lagrangian was a function of the generalized coordinate, generalized velocity and time. And when we solve Lagrangian equation, then we obtain second order differential equations. But in Hamiltonian dynamics, the generalized velocities are replaced by generalized momenta, and here we use two sets of first order differential equations rather than a set of second order differential equations. So for n generalized coordinates and n generalized velocities, we can write Lagrangian in more general form as L is a function of q1, q2, qk, qn, q1 dot, q2 dot, qk dot, qn dot, and time. Similarly, Hamiltonian can be written as it is a function of generalized coordinates, generalized momenta, and time. Now we will discuss generalized momentum and cyclic coordinates. For generalized momentum, let us consider a particle of mass m is, let us say, moving along the x-axis. Then its kinetic energy will be equal to 1 by 2 mx dot square, and let us say it is equation number 1. Here x dot is the velocity along the x-axis of the particle. Now if we differentiate it with respect to x dot, then we find del t over del x dot. It comes mx dot, and we can write it as px. It is x component of momentum. In more general form, we can say it equal to p. Let us say it is equation number 2. Now if potential energy is a function of the position coordinates only, then we can write del v over del x dot is equal to 0. So now we can write generalized momentum as, because p is equal to del t over del x dot and del v over del x dot is equal to 0. So we can arrange it like p is equal to del over del x dot t minus v, because del v over del x dot is equal to 0, so it will not affect the result. Now you know that t minus v, it is equal to Lagrangian. So p is equal to del L over del x dot. In more general form, for generalized coordinates, we can write the generalized momentum as pk is equal to del L over del qk dot. This is when we replace the Cartesian coordinates with the generalized coordinates. So here pk is called the generalized momentum or conjugate momentum or canonical momentum. As you know that for a conservative system, the Lagrangian equation of motion is given by d over dt del L over del qk dot minus del L over del qk equal to 0. Now if we see from equation number 4, we know that del L over del qk dot is equal to pk. So if we put here del L over del qk dot is equal to pk, then our equation becomes d over dt pk minus del L over del qk equal to 0, or we can write d over dt pk is equal to del L over del qk. So it comes out to be del L over del qk is equal to pk dot. This is equation number 6. So these two are very important relations. One is that pk is equal to del L over del qk dot, and the other one is del L over del qk is equal to pk dot. Suppose Lagrangian of a system does not contain a generalized coordinate qk, then you know that we can write del L over del qk is equal to 0. So we also know that del L over del qk is equal to pk dot. That means it will be equal to 0. That means pk is equal to constant. So when the Lagrangian of a dynamical system does not contain a coordinate qk, then generalized momentum pk is constant of motion, and here qk is called cyclic or ignorable coordinate. Thank you.